Spherical coordinates and spherical integration is going to be very important in this class, particularly in electrostatics, where we're dealing with charge configurations that have spherical symmetry. So what I'm going to do here is just a very brief sort of recap on things that you should have already learned in your vector calculus class about spherical coordinates and integration. If this isn't familiar to you at all, you should either look up a text on this, a good vector calculus, sort of a very simple vector calculus primer is called div grad curl and all that, or your vector calculus textbook. Or if you haven't had vector calculus, then you should really take this class after you've had vector calculus and multivariable calculus. Okay, so let's imagine we have some vector, some position vector r that's at some coordinate, the tip of which is at some coordinate from the origin x, y, z. So we would write this position vector as x I hat plus y j hat plus z k hat, as I've done here. And so basically what I hat, j hat, and k hat are, which again is something that you should have already covered, is basically they're unit vectors, which means they're vectors of length 1 that are in the direction of the x, y, and z axes respectively. Okay, so basically they are vectors of length 1, like as shown here. So basically, to define this position vector, then I multiply x, which is a scalar, times I hat, which is the unit vector, which gives it the actual direction, and then plus y j hat plus z k hat. So now let's imagine we want to go into spherical coordinates. Okay, so we want to now define basically our r in terms of r, which is now a scalar. It'll be a radius of a sphere, theta and phi, which are two angles. So what we're going to do now is to imagine that this position vector r sits on the surface of a sphere that has radius r, radius little r, like I've just written. So here is my sphere, and it has radius little r as shown there. So what I want to be able to do is somehow go from the Cartesian coordinates to these angular or spherical polar coordinates. Okay, so these are spherical polar coordinates. Or I'll just usually call them spherical coordinates, r, theta, and phi. So how do we go from one to the other? All right, well, let's imagine so what we're going to do is first define what theta and phi are. So theta is basically the angle that r makes with the z-axis, okay? One very, very important thing to keep in mind is that the way we define it in physics and the way the mathematicians define it are actually opposite. So theta is this angle here. In your math class, this would have been called phi. All right, so that's a little bit of confusion that you're going to have to bear in mind. And then if we drop, let's say, this down vertically onto the xy planes, imagine if you had a light and you casted the shadow of this point here down to the xy plane. Here, for instance, so I'm just going to redraw this. So let's say right here into the xy plane. So this would be sort of the shadow cast by this vector by the light sort of coming down vertically. Then my angle phi would be the angle between that shadow on the xy plane and the x-axis, okay? And this angle is going in a direction that's basically counterclockwise relative to the xy plane. So basically it's kind of an angle between the x and the y axes. Okay, so that's the way we define positive phi to be. All right, so that's how, and r, little r is just the length of this whole vector here. So how do we go, let's say we have r, theta, and phi, and we want to know what x, y, and z are. So let's start by saying, what is z? That's probably the easiest thing to figure out. So imagine here what we want to know is basically the z coordinate of this guy here. So if we basically draw a line that basically connects this back to the z-axis, this is a perpendicular, a right angle that comes out from the z-axis and basically attaches to this point here. This distance here is z. And so I have a right angle triangle. The hypotenuse is r. So it's going to be r either cosine or sine theta. And this is a good time to review this. If you're a little rusty on this, you should go back and look at your trig. So is it cosine or sine? Well, basically, this is the hypotenuse here. This is the adjacent. This is the opposite. So basically, it's going to be cosine because z is basically the adjacent. So basically, as you remember, cosine theta is adjacent over hypotenuse. So basically, it's going to be r cosine theta. One way I like to sort of check to see whether it's sine or cosine is I imagine if theta is really, really small. So if theta is really, like 1 degree, r is going to be almost parallel to the z-axis, right? So basically, z is going to be really, really close to whatever r is. So if r was 1 meter, z might be, 0.99 meters if theta was 0. And I know that when cosine is 0, I get 1. Okay, whereas if it was sine, I'd get something very close to 0, and that obviously wouldn't work. So I always like to take this limit of if theta was close to 90 degrees or if theta was close to 0. That's how I check. All right, so that's z. Now you want to get x. Okay, so I said that if I projected this, this position vector down here, and I had a light, let's say, shining down from the top, I would get a shadow cast into the xy plane at the equator. Let me just draw the equator really quickly. So then what's going to happen is that first of all, we can figure out what the length of the shadow is, and kind of just from the triangle I drew earlier. So here, this line here is basically parallel to this line here. They're basically copies of one another. So this length here was cosine theta, so it's pretty clear that this should be r cosine theta. So this length here, which is the same as this here, should be basically r sine theta. But that's not exactly what we want, because that's the length of this whole line here. What we want is its projection onto the x-axis, right? So we want basically this length here. So we have to do even a little bit more trig. So it's this length. And again, is it cosine or sine? Well, basically you can see again, this is adjacent. This is the hypotenuse here. So again, it should be cosine of phi. And again, phi is defined opposite. So in your math class, these two things would be switched, theta and phi. So when you're looking at your text, don't get too confused because they'll be your calculus text, they'll be opposite to how we usually define it in this class. And in all physics classes, we didn't just decide to be idiosyncratic. Okay, so for y, you can kind of do the same drill. So basically, it'll turn out that this length here is going to be, again, sine phi. I won't go through that whole deal, but basically, if I look at this triangle here, the length of this is the projection along the y-axis, even though I didn't draw this to be very parallel. So again, if you're a little rusty with when to use cosine or sine, take 10 or 15 minutes and kind of go through this and figure this out. Okay, so that's basically how we go from angles r, theta, and phi to x, y, and z. Okay, and you'll probably have to do this a few times in some of the questions we ask if we have, something, a spherical problem, and then we want the answer in Cartesian. This is basically how you go back and forth. All right, so then, these are the variables we use to write our position vector. The question is, how do we actually write the actual vector out in spherical? So you might expect a pretty natural thing to do is to write it as like r hat plus theta hat plus phi hat, right? That looks pretty reasonable. It turns out that this is actually wrong. Okay, so this is not how you write it. The one way you can see that is actually r is a length of a vector, so it might be 2 meters. But theta and phi are dimensionless, right? I mean, angles and degrees and radians don't have any dimensions. So you have something here that is basically having units, and something here that doesn't. So that doesn't really make any sense. So you can see kind of from there, at least, it can't be this. So I think at this point it should be one should probably think about what actually r hat, theta hat, and phi hat look like. So r hat is a unit vector. So again, it's a vector of length 1. I'm actually going to use green again. So it's going to be a vector of length 1 that is exactly parallel to the position vector. Okay, so r hat would look like this. Theta hat is basically pointing exactly in the direction towards, or depending where you are, away from the z-axis. So it's going to be kind of pointing up, sort of in the same direction as the theta angle is defined. And the phi hat vector is defined to be exactly 90 degrees to both of these, so that kind of only leaves us one option. So here, the way I've drawn it, it would be pointing sort of into the page. I'll attempt to kind of draw that badly. So you can imagine these three vectors are perpendicular to one another, okay? So you can see that, r hat actually is pointing exactly in the same direction as r. So basically, the way we would write it is basically as actually r hat. R hat actually already contains the information we want. It's pointing in the direction that's relevant. So basically r hat is the unit vector of length 1. If I multiply it by length r, I basically get this big red vector. Okay? Now, one thing that's really a little bit tricky about this is you have to remember that r hat is actually going to be a function of theta and phi. Okay, so it depends on theta and phi, whereas I hat, j hat, and k hat, the Cartesian unit vectors, don't depend on anything, right? And you can see this. So if I changed my theta and phi, so if I imagine I defined another position vector, let's say it's pointing out in this direction, right? So if I basically change my theta and phi so that they're pointing this vector out in this direction, r hat is always in the same direction. So if I called this r2, then r2 hat would point over this way. It has no dependence on r because r is just a length. R just tells you basically how long this vector is. And since r hat, theta hat, phi hat, and r2 hat are all unit vectors, it doesn't care about the length. It's always length 1. Okay? So one thing that's really strange is that r hat depends on theta and phi. So now if we had some, let's imagine some kind of electric field that we'll talk about in a couple lectures, and that electric field happened to have spherical symmetry. So imagine it was it was a sphere centered at the origin here. The way I could write the field would be some function of r, and the direction would be signified by r hat. Okay, so that means it's, in this case it would mean it would be pointing radially, and assuming f was positive, that would mean it's pointing radially outward. If f was negative, it would be pointing radially inward. Okay? So now I'm going to talk a little bit about how we would do integrals in spherical coordinates. So again, if we have a problem that has spherical symmetry, it's a much more natural and easier way to evaluate things. You could do it in Cartesian if you really wanted to. You would have to do some sort of parametric integral where you set your bounds of x, y, and z depending on where you are in space, and that's quite quite a bit of a pain. So spherical is a much easier way to go if we do have a problem that has the correct symmetry, the appropriate symmetry for that problem. Okay, so I will cover this again. This is something that I expect that you should have already seen. So again, let's imagine we have some problem where we have let's say a sphere, and the sphere has a radius r, and it has, let's say it's a sphere and we want to know the mass of the sphere. Okay, and the density may not be uniform, so it has some radius r. And the density could be, in general, some function of r, theta, and phi. For problems that have spherical symmetry, we'll generally, hopefully, deal with problems where it may just be a function of r and not a function of theta and phi. In this class, almost all the problems that you'd want to solve in spherical coordinates are basically the density is only just a function of r. But I will just start off with a completely general assumption that it could be some r, theta, and phi, and we need to integrate this density to get the total volume, right? And in Cartesian, the little volume elements you would have are would be little cubes. These wouldn't look quite like cubes, so if I look at what my volume element might be, basically going to be summing over things that look kind of like, these are tapered a little bit as they go into the origin. They look kind of like square conical sections that are truncated, if that makes any sense to you. So let's imagine we want to basically get the total mass of this sphere. So that is going to be then a triple integral, because there's three different position variables of rho, r, theta, phi, dv, right? And we need to know how to write dv in spherical coordinates. So if we set the limit, so again I said this had a radius r, so I'd integrate from 0 to r. One of the angles I'd integrate from 0 to 2 pi, and the other angle I'd integrate from 0 to pi. Okay. The reason for that is if I look back at this figure here, so for instance, I imagine this red point here. If I went from 0 to 2 pi, there would actually be two ways I could get to here. I could take theta at this angle I've defined here, and then basically the phi I've defined here, or I could actually sort of wrap around once, or I could sort of wrap around theta and phi, and I'd sort of double count. So if I had a factor of 2 here, I'd actually count twice the number of angles that I wanted. It's just, so basically we just have to, in order to sort of count all the points we want accurately, we set 1 to 2 pi and 1 to pi. But that should be something that you already probably remember from your calc class. So then, again, we're going to write, our density, our theta, phi. And then we're going to write out what dv is. That's a little bit more complicated. So it turns out to be written as r squared sine theta d theta, d phi, dr, okay? So this whole mess here is actually what dv is. All right, like I said, in almost all the instances that we're going to care about that have spherical symmetry in this class, if, and only if, so that's what this extra f is for, if r, theta, and phi is in fact only a function of r. Okay, so basically, has no angular dependence. Then this integral actually looks a lot cleaner. Okay, and we can see this right here. So I'm going to write m, and so I'm going to write, first of all, the integral from 0 to r. So basically, I'll have my rho of r here, which is only a function of r. It's not going to be theta and phi. So this is, again, a problem that has really, no matter what sort of angle I view it from, right? So if I rotated the sphere, everything would look basically the same. So there's no dependence on theta and phi. So it would be rho sub r, and then I have that r squared back there, and then this dr. So I'd have that here. I would have an integral from 0 to pi of sine theta d theta, and then an integral from 0 to 2 pi of d phi. So then integrating phi and theta are quite trivial. So this integral here, that just gives me 2 pi. And then this integral here, well, the integral of the indefinite integral of sine is minus cosine. So if I input the values here, this is basically -1, and this is 1, so it would basically be 2. Okay. So these respective factors give me a factor of 4 pi. So then my integral just looks like this: 0 to r, 4 pi r squared, rho sub r, dr. So we can then think of what this actually means. So 4 pi r squared, that probably sounds pretty familiar to you. If I have a sphere of radius r, that's just the surface area, right, of that sphere. So let's imagine we have these little spherical shells. I'm just going to draw that over here. So let's imagine I have a spherical shell here of radius little r. And it has some thickness dr. Kind of a lumpy sphere, but it'll do. Okay, so basically this thing has a thickness dr, and it has a surface area (4 pi r squared). And the density of this shell is going to be rho sub r, and it's going to be rho sub r everywhere, because on the shell, because it doesn't depend on theta and phi. It doesn't depend on sort of where I am on the shell. So then the volume of the shell is just going to be the surface area times the thickness, dr, because it's infinitesimally thin. We don't need to worry about sort of the difference in sort of the, the inner part of the shell and the outer part of the shell, because we're taking dr to 0. So this is basically the volume. And if you want to get the mass of the shell, that's just the volume times the density. Which is exactly what we have here in this integral, right? So what we're doing is basically we're summing over sort of nested shells, right? So that was for one shell, but really what we're going to do is kind of make, chop this sphere up into a whole bunch of like concentric little shells that are all nested inside each other. Then we're going to sum over all of them, right? So that's basically what we have here. So basically to get the total mass, we sum over the volume of each one of these little shells, and we go from the sort of the innermost shell at 0 to the outermost shell that has a radius r. So that's integration in spherical coordinates. That's basically what you're going to need to know. There's more general form up here. We basically won't encounter that too much in this class because most of the configurations we have will have perfect spherical symmetry. So basically the charge densities won't have any dependence on theta and phi.